This episode is brought to you by Brilliant. Click the link in the description below. Carbon nanotubes are cylinders that consist of rolled up sheets of single layers of carbon atoms. It's the same basis for graphene, and it goes back to 1991, which, weirdly, is long before the discovery of how to isolate graphene itself. The appeal of carbon nanotubes is their potential to dramatically improve energy storage and renewable energy, a topic that scientists have been attempting to tackle for decades. As it turns out, carbon nanotubes can be easily mass-produced already. So why haven't we seen the carbon nanotube revolution yet? Will they really be game changers? I'm Matt Ferrell. Welcome to Undecided. In the early 2000s, carbon nanotubes were all over the media, touted as being a breakthrough in energy potential and a solution for what sounded like endless applications. Everything from composite materials for large metallic parts like bikes, boats, and cars, to highly efficient transistors, nano-inks, biotech, and even space elevators. But after years of expected market rollouts, carbon nanotubes still haven't made the splash in the tech world that we were promised. As usual, the hype set expectations too high. Almost as high as the space elevator. So excitement dampened as time went on. But the key problem wasn't production of carbon nanotubes themselves. That had been available long before. Instead, it was with the precision and separation of the different types during manufacturing. To understand that, let's take a step back. Carbon nanotubes are essentially molecular sheets of carbon atoms, also known as graphene, which are arranged in a hexagonal lattice or honeycomb arrangement. It's a bit like chicken wire. These sheets are organized into layers and manipulated into cylindrical shapes. So basically, graphene is the basis for carbon nanotubes. You can't have carbon nanotubes without graphene. And these nanotubes can be designed and arranged in many ways. Single-walled carbon nanotubes are made up of, as you might imagine, a single layer of graphene. The way in which they're rolled up can impact their conductivity, but I'll get into that in a minute. Multi-walled carbon nanotubes are an extension of single-walled. They're made up of multiple layers of graphene, which better insulates their thermal and chemical properties compared to single-walled tubes. Double-walled carbon nanotubes are a combination of single-walled and multi-walled, with thermal, chemical, and conductivity properties that are intermediate compared to the other two. Depending on how the hexagonal lattice is rolled, it affects what's called the chiral angle of the final tube. It's how the hexagonal pattern spirals along the tube. If you follow the pattern across the diameter of the tube, you'll see three basic types: armchair, zigzag, and chiral nanotubes. And depending on the final design, it can make it act as either a metallic or semiconducting material. When manufacturing nanotubes, you usually end up with a mixture of types. The nanotubes have a tendency to clump into an entangled mess, and separating them apart has been a big challenge for mass-scale manufacturing. Remember, they're only a few nanometers in diameter, or about 50,000 times smaller than the width of a human hair. It's only when carbon nanotubes are grouped by purity, metallic or semiconducting, that they can be used effectively, which will ultimately advance all of those big promises that were made. Over the past few years, there have been some breakthroughs on how to effectively isolate carbon nanotubes after manufacturing, which has helped to push carbon nanotubes back into mainstream technology. Researchers at McMaster University adopted a polymer process which has been popularly used to reduce carbon nanotubes to only metallic components. The problem with this process was that it dissolved and washed away the semiconducting nanotubes. The researchers found a way to reverse the process, leaving semiconducting nanotubes behind and intact. A team of researchers from Northwestern University used the common chemical cresol to isolate nanotubes. Some methods use chemicals and chemical reactions to modify the nanotubes to force them to separate, but that can sometimes leave residues behind that alter their abilities. When they used cresol, they not only separated the nanotubes, but formed them into a thick, moldable gel. As one of the researchers pointed out, essentially this solvent system makes nanotubes behave just like polymers. It is really exciting to see cresol-based solvents make once hard-to-process carbon nanotubes as usable as common plastics. It's these types of breakthroughs that are going to take us from bulk manufacturing, where all of the nanotubes are tangled together, to isolated mass-scale manufacturing of carbon nanotubes. If we're ever going to make that space elevator, we're going to need a lot of isolated nanotubes. But where does that leave us with the actual products that we may see in our daily lives not too far from now? There are a lot of examples to pull from in just the past few years. One recent one is Vantablack, which is one of the darkest materials on the planet, absorbing up to 99.965% of visible light. Developed by Surrey Nanosystems in the UK, Vanta stands for Vertically Aligned Nanotube Arrays. It's that vertical alignment that traps the light that hits the surface from bouncing back out, which makes it look like a deep, dark void. Now, it may not sound like it has a lot of value, but it can have a big benefit for keeping stray light from entering a telescope and improving the performance of infrared cameras. On a less practical level though, I don't know about you, but I would love to see a car painted with this in person. And just this June, MIT researchers demonstrated how commercial silicon-based transistor foundries could transition to carbon nanotube transistors and save an immense amount of time. The fabrication process is up to 1,100 times faster than today's silicon process. Part of the reason for that is silicon transistors are manufactured at around 450 to 500 degrees Celsius, but carbon nanotubes can be manufactured at room temperatures. This will allow for layering of circuits for a three-dimensional chip, since you can build right on top of the previously fabricated layer. Now, if you tried that with a silicon process, you'd melt the previous layer. Three-dimensional chips are expected to outperform two-dimensional versions. But one of the more active areas for carbon nanotube research is around solar panels, and there's been a lot of interesting advances there. Just last year, Rice University had two interesting advancements. One team of researchers showed that double-walled nanotubes could have a dramatic impact on solar panel efficiency because of the double wall's efficiency at separating positive and negative charges to create current. Another team has come up with a method to improve solar panel efficiency by up to 80%. The fascinating part of this discovery is not that the nanotubes are actually improving the panel efficiency directly, but more in how it helps to capture unused potential: heat. To be more specific, infrared heat from the sun. Current panels are only capturing light and converting that into electricity. The research team designed an array of cavities patterned into a film of aligned carbon nanotubes. They're able to absorb and channel thermal photons and emit them as light. Essentially, they're converting heat into a form that the solar panel can then convert into electricity. It's kind of mind-blowing. Now, related to heat is another innovation that came up just recently. You may be aware that solar panels lose efficiency when they're too hot. Well, researchers at King Abdullah University of Science and Technology have come up with a system that keeps panels cool with no moving parts or excess energy drain. In their project, researchers developed a polymer that contains calcium chloride. When the material is exposed to humid air, it absorbs moisture and expands in size. In the latest research, they combined that polymer with carbon nanotubes to reverse that cycle and release the trapped water. When the gel was applied to the back of a solar panel, it was able to absorb moisture from the humid air at night and then slowly release it during the hottest parts of the day. The team saw panel temperatures reduced by 10 degrees Celsius, which improved efficiency by up to 20%. But this doesn't just apply to solar panels. Renyuan Lee, one of the researchers, said, "We believe this cooling technology can fulfill the requirements of many applications because water vapor is everywhere, and this cooling technology is easy to adapt to different scales. The technology can be made as small as several millimeters for electronic devices, hundreds of square meters for a building, or even larger for passive cooling of power plants." Another area where we're seeing carbon nanotubes making an impact is energy storage. The French company Nawa has created an ultracapacitor that's going into mass production. While batteries like lithium-ion offer far more specific energy storage, they charge and discharge far slower than ultracapacitors. Capacitors can charge and discharge in an instant, so they're perfect for quick bursts of huge power. They can also last for 1 million charge cycles. But again, the downside is the amount of energy that they can store and for how long. Nawa's new ultracapacitor sits somewhere in between a capacitor and a battery. It can store about 5 times more energy than a competing ultracapacitor, but charges in seconds. It's using vertically aligned carbon nanotubes that are grown with a patented method for coating 2 sides of aluminum or copper foil. Some of the first places that they expect to see this technology getting used is in power tools, automated vehicles in factories and warehouses, and possibly electric vehicles. All areas that require high energy use with limited charging downtime. The team at the Advanced Materials and Bioengineering Research Center at Trinity College in Dublin have created a carbon nanotube composite electrode for use in a lithium-ion battery. They're able to build cells with a specific energy of 480 watt-hours per kilogram, which is around twice of a normal lithium-ion cell. Companies like Nokia Bell Labs, which is a partner of the research center, are interested in the breakthrough for powering 5G phones and the broader network. But this type of breakthrough could easily make an impact on grid storage and electric cars as well. Carbon nanotubes may have fallen out of the limelight for a while, but there's been a lot of interesting advances over the past few years that's reigniting interest. In my case, I'm really interested to see how these advancements impact solar and energy storage, but as cool as some of this is, we're still not getting that space elevator anytime soon. Now, the more I've been diving into these scientific topics for these videos, the more I've been wanting to get a better understanding of the principles behind them. And that's why the Science Essentials course at Brilliant has come in so handy. The course walked me through atoms and potential energy, which is all about storing energy and how to use it later. And even if science isn't your thing, there are so many other courses to choose from. They have more than 60 courses including topics in mathematics, statistics, and computer science. I don't know about you, but learning from rote memory was never my thing. I always did better when I was taught the fundamentals so I could apply those techniques in my own ways. And that's Brilliant. The courses break down complex concepts into digestible, bite-sized chunks. You're not learning by memorizing formulas, you're learning by doing and applying what you're learning with fun and interactive challenges. So go to brilliant.org/undecided to sign up for free. The first 200 people will get 20% off their annual premium membership. Thanks to Brilliant and to all of you for supporting the channel. Now jump into the comments and let me know what you're looking forward to the most with carbon nanotubes. And as always, a special thank you to all of my patrons, and a big welcome to new producer, Niels Bolt Wilson. If you like this video, be sure to check out one of the ones I have linked to right here, and be sure to subscribe if you think I've earned it. And as always, thanks so much for watching. I'll see you in the next one.